Good morning, everyone. Welcome to the AIPG Lunch and Earn Seminar for June of 2023. I'm Aaron Johnson. I'm the Executive Director of AIPG, and I'm really glad to have all of you here today. Just a couple of quick housekeeping notes. If you have questions, you can feel free to drop those into the chat box, and we'll go through the questions as we get to them toward the end of the talk. If you have a question that you'd like to give in person, we can certainly unmute you and give you that opportunity at the end. Second, the CEU certifications are automatically generated provided that you stay online for the webinar. So there's no need to ask us for a certificate. We will mail that directly to or email that directly to the address you used when you registered for the event. I'm really excited about today's talk. Today we have Sean Kosinski and Bill Cutler. They're going to be talking to us about the Salar del Hombre Muerta deposit in Argentina. Sean has a CPG, works with Livent, did his schooling at University of Nevada, Reno. And Bill has a PhD. He's a Hawaii Rainbow and works with Integral Consulting. I don't want to go any further into the introductions. Bill and Sean, I'll let you take it away now, and you can tell us a little bit more about yourselves and get the ball rolling.
Yeah, thanks, Aaron. Yeah, before we get started, I just wanted to say thank you to the whole AIPG organization. They've been outstanding in working with both Bill and I to get our CPGs and have been a great resource for us as professionals. So thank you to you and your team. I'd also like to give thanks to someone who's not mentioned on our slide deck, our colleague Michael Sweetnam at Integral Consulting. He has done a lot of work behind the scenes to help prepare the slide deck and has done a lot of the technical work. I think he's planning on using some of this information to present at another conference in the coming months. So I'm Sean Kosinski. I'm a CPG with Livent Corporation. I recently joined Livent as their global resource development and optimization leader in April of this year. Prior to that, I'd been a consultant for them for the better part of 10 years before joining Livent. I was with Integral Consulting, where I worked with Bill Cutler and Michael, as I just mentioned. So with that, I'll turn it over to Bill to introduce himself.
Yeah, hi all. Bill Cutler, a geologist working with Integral Consulting. If you don't know Integral, we're a US-based science and engineering consulting firm with a real strong geoscience group. And we've been supporting Livent and their predecessor, FMC Lithium, for over 10 years on this project down in South America. So with that, Sean, I think we'll lead it off.
Yeah, so as Aaron mentioned, the focus of this talk will be on the Salar del Hombre Muerta deposit. It's a lithium brine deposit in northwest Argentina. We've been producing lithium out of this Salar for the better part of 25 years. We consider it one of the best resources on the planet. It's has a very consistent lithium brine grade, and it's one of the highest purity deposits in the world. In the background, you could see the western subbasin. We'll be talking about this a lot in the coming slides, but the western subbasin of Salar del Hombre Muerta in the foreground is the eastern subbasin, and we're looking, in this particular photograph, we're looking west. So just to provide a little outline on today's talk, Bill and I are going to tag team this talk. I'm going to start off by providing an overview of the Livent Corporation, our operations, and get into a little bit about lithium ore. After that, Bill's going to take over and talk about some of the work he's been doing at Integral over the years to support us. And then towards the end, I'll touch upon some of the future activity we have planned. So this image, I'm not sure if our video feeds are covering this up, but there's a picture of a vicuña in the foreground and some of our facilities in the background. This picture, I took this picture a couple of weeks ago. Vicuñas kind of look like maybe a cross between maybe look like a miniature camel or a llama, but they're a species that have adapted to the harsh conditions up here in the Altiplano. And typically these things are very, very skittish. On the day that we were there, I was with somebody from the mine who'd been working there for 20 years, and he said he's never seen them get this close to the vehicle, which is about a meter and a half away. They're really skittish, and if you get too close to them, they're the biggest cause of death for vicuñas are heart attacks. They get pretty scared and nervous when anybody approaches them. So a little bit about the Livent Corporation. We can trace our roots back to the early 40s when it was the Lithium Corporation of America that got started in Minnesota with lithium hydroxide production. Shortly after that, in the 1950s, we collaborated with the U.S. government to develop some specialty lithium chemicals for applications and for military applications and for ceramics, glass, air treatment, among other things. But at this point in time, lithium as a key ingredient in energy storage or battery applications really wasn't on the horizon until a little bit later. 1954, the Bessemer City lithium hydroxide production facility was started. This facility is still in operation today. It's the primary U.S. operation for lithium hydroxide for Livent, among other lithium products. The key difference being that it's undergone a major expansion in recent years. In 1954, the FMC Corporation acquired Lithium Corporation of America. And shortly thereafter, we worked with Sony to develop one of the first lithium-ion batteries for their portable handheld camcorders, if you remember those from the early 90s. Recognizing a need for additional resources, FMC at the time sent a team of exploration geologists to Argentina to identify good resources, and they honed in on the Salar de Muerta for its unique characteristics. And after a exploration program in the early 90s, commercial production began in the late 1990s of lithium products. Other key dates, in 2018, the FMC Corporation divested its ownership in its lithium division, which allowed Livent to become its own corporation. And in about 2020, Livent had acquired a 50% interest in the Nemaska project, which is a hard rock spodumene-based deposit in remote northern Quebec. So we're a vertically integrated lithium specialty chemical company, which means that we create specialty lithium chemicals from the source. Our resources, as I mentioned, we have two key resources. The one in Argentina, which is the primary feedstock for all of our manufacturing and products. That's the Salar de Muerta. We do have the 50% interest in the Nemaska project or Whabouchi mine in northern Quebec. That site's in a phase of advanced exploration right now. It's not currently creating any lithium. So our focus will be on Project Phoenix, which is the Argentine operation where lithium brine is extracted and lithium carbonates are produced. Lithium carbonates used in electric vehicles and portable electric storage devices. It's also used as a feedstock for lithium hydroxide, which is a higher performance battery application. It's used for specialty salts and pharmaceuticals. Some of the lithium brine at Project Phoenix is directed to our Güemes facility, which is located about 45 kilometers north of Salta, Argentina. The lithium chloride's used onto itself for air treatment and purification, but it's also used to help develop some specialty lithium metals, including butyl lithium, which is an additive that's used in rubbers and other polymers for increased performance. It's used in the agrochemical industry and pharmaceuticals. So Hombre Muerta is located within the lithium triangle. If you've been paying attention to lithium as a commodity, it's This area is referred to quite often. It's an area that contains most of the world's lithium reserves, and it's bound by a extremely large lithium deposit in Bolivia. The easternmost extent extends into Argentina, and the western into Chile. I've identified a couple of key resources within the triangle, the northernmost one being Salar de Uyuni, I hope I pronounced that right. Salar de Atacama, which a lot of people know about in Chile. Hombre Muerta is on the southern portion of the triangle, and then Olaroz Cochari is sort of in the center of the triangle in Argentina. This triangle exists because the conditions are favorable for lithium brine development. There's a really good paper from the USGS about 2013 that describes the conditions necessary for continental lithium brine occurrences, and it has to meet some key criteria, including an arid environment. So this is a really dry portion of the world where evaporation greatly exceeds precipitation. You have to be in a closed or endorheic basin, so all of the water that flows into a particular watershed has to leave by evaporation. That is, by definition, what a salar is. There has to be some tectonically driven subsidence, nearby geothermal or igneous activity, suitable lithium source rocks, and you need an adequate aquifer to extract lithium brine from, and then time to concentrate these lithium brines into something economic. So all of those conditions are favorable within this triangle. Salar de Hombre Muerto is generally where the star is shown on this figure on the right. It's within Catamarca province, but the northern extent taps into Salta province to the north. The salar itself, the floor of the salar is at 4,000 meters above mean sea level. This is a close-up of the salar. When I say the salar, we're generally referring to parts of Salar de Hombre Muerto, two parts, and they really represent the two end members of salars, one being a mature salar and the other being immature. The western subbasin is a characteristic mature salar, and the eastern subbasin is a really good example of an immature salar. The key differences between them being that mature salars tend to have a well-developed halite nucleus. The hydraulics in a mature salar are very favorable for brine development, in that the hydraulic conductivities in immature salars tend to be very, very high, at least in the upper 50 to 100 meters or so. And that allows brine extraction to occur uniformly across the salar, whereas in the eastern subbasin, which is a immature salar, you have a higher percentage of clastic materials, which can reduce the hydraulic conductivity and require more production wells to produce an equivalent volume of brine than it would in a mature salar. And then generally speaking, mature salars tend to have a more consistent or homogeneous water quality profile. Some of the key features at Project Phoenix that we'll be talking about are the well batteries. We've been producing all of the lithium from the western subbasin from a battery, a network of 6 production wells since 1997. I think that's really remarkable. Those wells are drilled to about 30 meters below ground surface. So for 25 plus years, almost all of our product has been produced out of those 6 wells with very little drawdown. We're talking on the order of maybe 1.5 meters in a production well. To increase production, we added a couple of wells called the secondary well battery off to the south here. And we use a direct lithium extraction process. I'll zoom in on this area here in just a minute, but that process allows us to use the brine and essentially strip the lithium from the brine. And in doing so, it requires that we use water. So this is a little bit different than a conventional evaporation pond-based lithium brine operation. And using that fresh water and brine, native brine, that mixture is directed without lithium back to a lagoon where it's allowed to infiltrate and evaporate from the ground surface. Currently, we're using water from the Rio Trapiche. It's the label is kind of cut off here, but you can see the alluvial fan where my cursor is. The Trapiche flows at around 300 cubic meters per hour and supplies all the fresh water for Project Phoenix. We're planning to expand our operations, which will require us to seek other freshwater resources. So we've explored the Rio de los Patos. This watershed is much larger than Trapiche and flows in the surface waters here are around 20 times or 6,000 cubic meters an hour. So a little bit about direct lithium extraction. To my knowledge, we're the only company that operates a DLE process at commercial or production scale. There are a lot of companies that have demonstrated this at the pilot scale, but to my knowledge right now, we're the only one that's been using it. We have been using this process since 1997, but the process itself requires lithium-rich brine from the Salar to be directed to either a pre-concentrate pond or directly to the SA or selective absorption plant. At the plant, fresh water is used to separate the brine mixture from lithium. And as I mentioned in the preceding slide, the mixture of spent brine and fresh water is directed to the surface of the Salar where it's allowed to evaporate. And one of the advantages of the direct lithium extraction process is that it speeds up the time to concentrate the brine without the need for very large evaporative ponds that take up quite a bit of surface area. And we don't use any solvents or hazardous chemicals in our process. So after leaving the SA plant, the enriched brine is sent to FSB ponds, which I apologize, I don't have them shown in this figure, but they're much smaller than what you would expect to see at a conventional evaporation pond-based operation. They're designed to further concentrate the brine after it leaves the SA plant before it's directed to either our carbonate plant or is shipped off-site to our Güemes facility that I mentioned earlier about production of lithium chloride. So if you've seen any pictures of Project Phoenix in years past, you'll notice this is a relatively recent photograph, and it shows that there's a lot of construction activity ongoing. We have plans to expand our operation to about 100,000 metric tons of lithium carbonate per year in the coming years. So I included these because, you know, we're giving a talk to the Institute of Professional Geologists. So this sample was taken from the Whabouchi mine site, the one I mentioned in northern Quebec. This is a pegmatite sample with a characteristic spodumene crystal shown in pale green. In the center of the sample, you can see some garnet off to the side. Spodumene is the primary lithium-bearing ore for hard rock deposits. It's a lithium aluminosilicate pyroxene. And the host rock, if you will, for the brine operation, at least for the western subbasin, is halite. It's a sodium chloride table salt. But here you see there's some really prominent large growth crystals. You can tell I'm not a true geologist because there's not a scale or a pencil or something to give you some perspective here, but the center crystal is on the order of around 3 inches long. You'll notice too that there's some inclusions of ignimbrite sediments in some of these samples here. At this point, I'm going to turn it over to Bill to talk about the geology of Salar del Hombre Muerta.
Thanks, Sean. So Sean mentioned at the beginning that there's some key characteristics that result in these lithium-rich brine deposits in salars. First of all, that endorheic or terminal basin where any water flows end up and evaporate under an arid climate, and generally a tectonically driven subsidence is occurring in the region, which results in igneous and geothermal activity. You need to have lithium in either source rocks or hydrothermal waters that then get transported with surface water or groundwater into the endorheic basin, which is essentially the reservoir or an aquifer. It's essentially the same thing in this case. And then you need time to concentrate the lithium to commercial grades. And the interesting thing about lithium is as you're precipitating out the various evaporite minerals, the lithium does not end up in the mineral precipitate. It's retained in the brine, even through the last stage of sodium chloride precipitation, and therefore you get higher and higher lithium concentrations as all the other precipitates occur. The lithium remains in the brine, and that's where it's extracted. So next. Just a little bit about the physiography of the area. Here on the right, you've got an air photo and then a profile, an elevation profile. We start in the western subbasin at the endpoint A at about 4,000 meters or 13,000 feet. And then this cross-section goes east into the eastern subbasin, that immature basin, up the Los Patos River Valley, and to the endpoint B, which is an extinct volcanic caldera called Cerro Galán, which is at 6,100 meters or 20,000 feet. Generally, the area that you see in this photograph is also the watershed from which the surface waters and groundwaters flow towards that endorheic basin of the Salar del Hombre Muerta. Lastly, the precipitation is low in the area at the salar itself. It's about 100 millimeters or 4 inches per year. It is a little higher in the precipitation is a little higher in the higher elevation areas surrounding the salar. Next, Sean. Here's a photograph that when Sean and I were flying in and out a couple of years ago. On the left-hand side, you'll see just a little bit of surface water on top of the eastern subbasin of the salar. And then kind of in the center, you'll see some eroded volcanic features, some volcanic mountains. In the backdrop, you'll see some uplifted Paleozoic and Precambrian sediments. And just under the wingtip, you'll even see some snow on some of these higher elevations that are getting up towards 18,000 feet or so. A lot of faulting in the area that causes uplifted and downlifted sections that create these endorheic basins. Kind of in the bottom left, just bottom left of the center, you'll see some eroded, scaly looking material. That's an eroded ignimbrite flow from the volcanic centers. Those are basically pyroclastic flows of pumice that are common down in that area. So it's an intriguing geologic scenario and quite complex. Next slide. Just for regional geology, we're looking at a section of the Andes here. The Puna Plateau, which is this generally the big flat area where the lithium triangle exists, is east of the volcanic arc above the subducting Nazca Plate underneath South America. The local volcanic activity has been even from Miocene to present. It's still quite active and in the general area. There's a combination of some eastern trending volcanic chains, but most importantly, there's a series of north to northeast trending faults. You can see the fine lines on the map on the right. Those are the major faults. Obviously, many more faults associated with it. Dominantly reverse faults, but with normal and strike slip faults that cause these structural blocks and downdropped portions that create the endork basins. Typically, again, these basins in the salars themselves, the surface is extremely flat, as you expect, expansive with little or no perennial water or vegetation. Next. Here's a geologic map. It's too complex to go through on this talk, but just to give you a sense of where the Salar sits with respect to surrounding geology. Sean, you can maybe show your cursor on the western subbasin where Livent has their concession. Geologically, it's mapped as a Holocene evaporite deposit. And then the eastern subbasin, which has a slight connection through a little gap between some uplifted Paleozoic sediments and some recent volcanics. And then you can see also there are some evaporites and clastics at low levels that run from the south from the eastern subbasin along the Los Patos River Valley. Within these endork basins, in addition to the evaporites, you will get clastics, you will get eroding clastics, alluvium that comes in off the adjacent hillsides that work their way into the basins, predominantly in the eastern subbasin, but there are some alluvial fan sediments that penetrate into the western subbasin as well. And you'll also get some tuff horizons from some airfall tuffs and such that have occurred historically along with the evaporite deposition. Next. So the evaporite distribution within a basin, there are a number of different minerals that are precipitated out within these salars. There's a general pattern of the first precipitates being carbonates through borates, sulfates, and then chlorides, sodium chloride, halite as the last precipitate. They generally follow a pattern of the early precipitates on the boundaries of the salar basins, and then the last precipitate being the sodium chloride in the centers. The eastern subbasin, we talked about this, Sean talked about it a little before. It's considered immature in the sense that it has more of the early precipitates. It's got more clastics. It's about 350 meters deep, so it's still a significant basin with good lithium brines present. The western subbasin is more of the mature salar, and you can see with that pattern of kind of squares, that squared pattern is a halite core in which in the center of that Livent has their production wells. We believe it's about 900 meters deep. Not exactly sure, but that's based on some gravity geophysics that was done some years ago. Next slide. Oh, excuse me. Before we go there, we're going to look at a cross section, that heavier black line that runs from the western subbasin over to the eastern subbasin on the next slide. And if you look at that kind of cartoonish cross section on the right, it's much simplified, but does give you a sense of the fact that the fault bounded basin with Paleozoics and Precambrian rocks bounding it, and then the recent sediments within the basin. The eastern subbasin, Subcuenca Oriental, is dominantly carbonates, borates, and clastics, along with a small halite core, which isn't shown in this cartoon. And then to the west, the western subbasin, maybe as deep as 900 meters deep, has some carbonates and sulfates along its perimeter, but dominantly, as a mature salar, is dominantly a big sequence of halite. Next. If you look out at the Salar from standing on the edge, it is certainly very flat. It will flood at times during the spring runoff, times of heavy precipitation. It will temporarily flood and then evaporate away. The brine water table during the dry period is only about 1 meter to 1.5 meters below this salt crust surface. So you certainly don't have to go down deep to engage with the brine. We talked about, next slide, I believe will show a picture of the Rio de los Patos. This was the river that comes from the south and enters the eastern subbasin. This is the primary water source. It has a few parts per million lithium. It contributes the lithium into the system in large degree. There's Sean sitting on the edge of the river during it's probably one of its summer low periods, and Sean sure wishes he had his fly rod because it is one heck of a nice brown trout stream. Next slide, please. So before I hand it back to Sean, I'm just going to go over real quickly about what was done back in the early 1990s before development and production started to ensure that the resource was adequate for FMC at the time to make the change in its lithium resource from the hard rock mine in North Carolina to the brine-based resource in Argentina. So in the early 90s, they drilled a number of boreholes, geologically logged them, cored them predominantly in order to do analysis of effective porosity and to get brine samples for chemistry. They did downhole geophysical logging, some packer testing, and some geophysical surveys to try to determine the bottom of the basin, the bedrock at the base of the salt, and installed some pumping wells to ensure that there was adequate hydraulic conductivity to produce the resource. Next slide. The results of that work were promising. There were almost 900 core samples that were analyzed for specific yield, which is basically the same as effective porosity. You'll also hear the term drainable porosity. That's the interconnected porosity from which the brine can be drained or pumped. And the specific yields averaged about 7 or 8%, even to depth at 60 meters, which was the deepest samples that they analyzed. So that certainly was promising. The lithium grades ranged from about 500 to 800 milligrams per liter, and averaged just a little below 700 milligrams per liter. And some of the samples that were taken down to about 90 meters were equally promising. So it looked like there was consistent lithium grade throughout at least that upper 100-meter section. Next. From that, mineral resource estimate was calculated. There were a couple of different techniques used. They took the results of the porosity and lithium concentration. They did some kriging. They also used back in the day, and actually Integral subsequently later on in the process redid some of these calculations using single polygons and what's called Tyson polygons, where you each borehole has its polygon of all the area which is closest to it, and then through various layers from the surface down to depth, broken up into these polygon volumes. Through this process, doing it in multiple different ways, similar total lithium resource estimates were about the same for each method, so we were consistent with that. But just so you understand, it's not a complex calculation to figure out what the mass of lithium is. The resource calculation is basically you take the volume of the reservoir, you multiply it by the specific yield or effective porosity, and then you multiply it by the concentration of lithium in that volume, and that's the lithium mass, and then you sum them up across the various polygons, however you've broken it up, and that gives you your total lithium resource. So with that, I'm going to pass it back to Sean. He's going to talk about some of the further work that's been done more recently on resource and reserves at the Salar.
Yeah, thanks, Bill. So in 2018, as I'm sure a lot of folks on the call recall, the SEC had issued a modernization requirement for companies that are publicly traded on the SEC to come in line with really the rest of the world and its reporting standards for mineral resources and reserves. It was at this point in time that we reevaluated the resource at Hombre and Muerta using a little bit different technique than we had previously. So, if you were thinking about this, developing a resource in a linear way, you would collect information during your exploration program that you would in turn use to inform your resource estimate. In our case, we've been, successfully extracting lithium for over 20 years, and we're attempting to reestablish what the resource was. To do that, we had a monitoring well network of over 35 wells screened at different intervals, and used the water quality data from those wells as the basis for estimating the resource. We use that information in combination with the specific yield characteristics that were measured historically, and as part of a exploration program that was completed in 2012. What we found is that if you were to compare the resource estimate and subtract the amount of production that occurred since the most recent estimate was developed back in 2016, if you remember Bill's slide previous to this one, that the estimates were nearly identical. So we had a lot of confidence that we were able to reproduce the resource estimate this way. This was published in our resource and reserve report, an SK 1300 compliant report that was issued in February of this year, where we had measured and indicated resources of about 1.3 million metric tons lithium, or 7 million metric tons LCE, and inferred resources of 2 million and almost 12 million respectively. So this resource was used as the basis for estimating reserves. So this is really the starting point upon which we estimate the reserves. We did this using industry standard, publicly available groundwater modeling software. So we use CWAT, which is a combination of both ModFlow and MT3DMS. And really this is a tool, it's a bookkeeping tool to track the accumulation or depletion of lithium in response to operational considerations. So for our reserve, we were estimating our production where we're targeting 100,000 metric tons LCE per year from years 23 and beyond, or 2030 and beyond, for a 40-year life of mine period. In my opinion, we were conservative in establishing the proven resource as lithium that had originated from the measured interval in years 0 through 10, and probable in years 11 through 40 for resources that had originated as either measured or indicated. Our total and proven and probable reserves as of the beginning of this year were 731,000 metric tons lithium, or 3.8 million metric tons LCE. What we have going forward, we are undertaking what we're referring to as a deeper exploration program. So this cross section shows you the vertical extent of the Salar del Muerto Western Subbasin. In the purple cylinders that you might see in the background, transparency, are different boreholes that were drilled at different points in time, and some of the deeper ones that we have extending down to 300 meters. But the resource as it's currently classified is such that the 0 to 40 meter interval, essentially where we have been producing brine for the past 25 years, is the measured interval. We have indicated resources down to 100 meters and inferred down to 200. We're looking to expand the resource by doing additional drilling, geophysics, downhole geophysics, and sampling to expand the resource at depth. You know, one of the things we're looking for in particular is, you know, we recognize that in salt deposits, it's likely that the porosity is going to decrease with depth. So we're trying to identify some intervals of clastics that may be present and that would allow for a higher porosity and in turn greater production as we get deeper into the resource. That concludes our presentation for today. It looks like we have some time for questions. If anybody has any, I'll turn it over to Aaron to moderate that piece.
Thanks, Sean. I appreciate it. And thank you guys for a fantastic and informative webinar. I'm going to kick off the questions really quickly just by asking, when you do your calculations on your reserve and on your estimates, are you assuming that your recovery is going to be pretty near 100%, or what do you expect in terms of recovery through the pump evaporation and then processing piece?
You want me to take that, Bill?
Yeah, Sean, go for it.
So the recovery through the SA plant is quite high. It's on the order of 95%. Where you see the biggest losses are in when we do route some of the brine to a pre-concentrate pond. That wasn't always the case, and it's not required for our process, but we noticed a huge decrease in efficiency when we started using those ponds just due to the leakage back into the Salar. Typically, a typical pond, evaporative pond-based system might have efficiencies between maybe 60 and 70%.
Chuck Spalding has a question, I think, that follows up, and that would be two-piece. One about whether or not evaporation ponds are lined or how they're lined, and the second is whether or not you've seen or experienced any subsidence related to your extraction.
Well, on the first question, I'm not a pond guy. I know there are different geotextile membranes that are used for different applications. Typically, you would use a more, a more rigorous, more competent, thicker geotextile for your finished ponds than you would perhaps on a pre-concentrate pond, which is much larger in extent than your product ponds, so to speak. And it would in turn reduce the amount of infiltration with, with better quality liners. To answer the second part, subsidence, we have seen some differential, I wouldn't call it subsidence, but in areas where freshwater has encountered the native halite near ponds, you do see some pocketing where the salts are dissolved, and that compromises the integrity of liners in some places, but not subsidence like you would see in a conventional sense where say a clay unit was being dewatered and subsides as a result of that.
Okay, and I see one other quick question that was in the chat from Oris Patterson. He asked if the fire in your North Carolina plant on Sunday impacted your production of lithium carbonate.
No, the fire that occurred is, I don't have a lot of information about that particular incident, but there was a fire at the Bessemer City facility that's currently being managed. It's my understanding that that plant processes lithium hydroxide and some other specialty lithium chemical compounds, but not lithium carbonate. Lithium carbonate is produced at our facility in Hombre Muerta.
I see Peter Muller has his hand up. Peter, you've been unmuted. Please go ahead and unmute yourself and fire away.
Yeah, thanks. I was just wondering, I was surprised to hear that you need you need fresh water in your DLE process. Can you give just an estimate of the ratio of fresh water to brine that is required?
Roughly 4 to 1.
4 times more
brine than
4
fresh
times
water.
more brine than fresh water.
It's probably even higher than that. It's probably 6 to 1, Peter.
Great, thank you. Interesting. I didn't realize that is. Are most DLE processes in your understanding require that much fresh water?
It's my understanding that the other DLE processes that are being evaluated require fresh water. But I'm also not privy to all the details. A lot of these are proprietary systems. And so I think as a matter of course, the direct lithium extraction process is one by which lithium is absorbed or filtered onto a media that requires some additional rinsing. And that's where the need for fresh water comes in, at least in our process.
Okay, great. Thank you.
Yep.
All right, I see William Feather or Gail Wilson or both have their hands up. You're free to talk. Please unmute yourself and ask your question. Are you there? I see he's put it in the chat. So in the chat, he asks, is there a correlation between lithium and volcanics?
There is. Bill, you want to take that one?
Yeah, well, certainly, I would say that the geothermal activity in this area seems to be the dominant source for the lithium. So volcanic activity and current kind of geothermal waters seem to be critical. If you go upstream in the Rio de los Patos, there's a tributary that comes off the side, which is Rio Agua Caliente, hot water, so there is geothermal sources that feed into the surface water, which are we believe are bringing the lithium from depth, whether it's stripped from some source rock by the hot waters that it travels through, or exactly how it comes into those geothermal waters is uncertain, but it appears that the geothermal waters discharging into the surface waters that then lead into the Salar and evaporate is the process that leads to the deposit. So yes, the geothermal volcanic activity is critical to making this resource.
Thank you. David Edelman asks, what is the total flow rate from the production wells?
Total flow rate from production wells is on the order of, I want to say 2,400 cubic meters per hour.
Okay. And Bill Agee asks, could you provide maybe some more details regarding the DLE process, things like the technology, yield, et cetera? I think the main question is, could DLE on a larger scale replace evaporation ponds?
Well, I can answer the second part. I do think it has the potential to replace evaporation ponds. I'm reluctant to get into too much detail about our process because it is a proprietary one, and as a relatively new employee, I don't want to jeopardize my career providing too much detail.
I will also say that the overall environmental footprint of a DLE system, it's obviously less intrusive than creating the very large evaporative ponds. So it does have advantages, not just perhaps from process engineering, but it certainly has some environmental advantages as well.
Martin Cassidy has raised his hand. Martin, you should be able to go ahead and ask that question.
Can lithium brine be extracted from the borate evaporates?
Well, I'm not 100% sure, but I don't believe that the borate minerals will have the lithium bound in the mineral structure, but the eastern subbasin, which has clastics, borates, carbonates, and some halite, does have lithium-rich brine. So wherever you find porosity and permeability, be it within an evaporite mineral sequence that has primary intercrystalline porosity or secondary fracture porosity, or be it porosity within interbedded clastics, wherever you have brine in a porous, permeable fabric, then you should be able to produce it and get access to that lithium.
Thank you.
Riley Millington asks, what did the earliest exploration programs look like?
You wanna take that?
Well, Sean and I weren't there for the earliest ones in the early 1990s. I actually was working for FMC in North Carolina and shutting down the hard rock mine at the time, and I wasn't down there. I knew that activity was ongoing back in the early 90s, but I wasn't involved in it per se. I believe it was basically drilling rigs out there. They must have had some infrastructure for on-site laboratories and all. Sean, if you have anything further to add to that, of course, we weren't around during that time period.
Yeah, based on the reports that we've reviewed, it's, the exploration program it probably set the bar for future brine exploration programs. Involved core drilling, hydrochemical analyses, hydrologic testing, lysimeter testing, so measuring rates of evaporation. It was a full-blown baseline hydrogeologic characterization with coring to estimate specific yield and collect discrete lithium brine samples.
Great. Nerio Mendoza asks if you can tell us what the total production cost would be to get a ton of lithium. I wouldn't be in a position to disclose that information. That's fair. Another question from David Edelman. He says, I heard that there was little drawdown in the production wells, but also that you're exploring deeper and hoping for more permeable clastic sediments. Why not just pump more from existing wells?
That is actually the strategy. The point being, we know that we can develop lithium brine. We can produce lithium brine from our shallow intervals. We've demonstrated that, and as part of the expansions that we have underway, we are targeting the upper intervals. But I think in a good faith effort to understand the resource as a whole, we are exploring at depth. It's not that we're intending to necessarily put production wells 300-400 meters below ground surface, which a lot of other brine operations do. But we want to see what that potential looks like for our resource.
Okay, and then one final question, and that'll be, I'll close this out. I know that you're looking at a system where you have migration of lithium-rich fluid into the system. Do you have any idea of what the influx and outflow rates are? What's your sort of flux through the system? How much lithium brine might you be losing? How much is coming in?
Yeah, so Rio Aguas Caliente, we measure concentrations of lithium brine, dissolved lithium in that river at around 4 milligrams per liter. And that flows at probably a couple hundred cubic meters an hour. Lithium is conservative in the sense that it's not creating any secondary mineral precipitates, so we're not losing anything other than by the extraction of the brine itself.
So you see very little in the way of outflow from the system.
Right. The Western Subbasin in particular is the terminus for the entire watershed. So everything's flowing in from basically all directions.
Fantastic. Well, I think that, oh, we got one more. A question is, do you have an idea of what the total dissolved solids are in those brines? And then we'll finish it up.
Yeah, well, they're if I remember correctly, the density of brines are about 1.2. Is that right, Sean? So I think they're around almost 10 times seawater concentrations. 1.25 perhaps. I can't recall exactly. Do you remember, Sean?
Yeah, around 1.22. It's around 330,000 milligrams per liter TDS.
Well,
Yeah, about 10 times seawater.
fantastic. Fantastic. What a great talk today, guys. I really appreciate it. Sean, Bill, thank you so much for sharing your expertise with us. Thank all of you who attended. We will be sort of shifting to more of a hydrology, surface water, and environmental focus over the coming months. The next talk will be from John Fontana. He'll be talking about site characterization when we have surface contamination. So I encourage you to see that. That will be the last Tuesday of July. But we will try to intersperse on occasion the continuing economic geology talks, because I know the demand for minerals will increase as we continue to transition toward a lower carbon energy production grid. So thank all of you again for coming, and I hope to see each of you at our next event in July.
Thanks, everyone.
Thanks, guys.
Thanks, everyone.